The most relaxing facts about magnets to fall asleep to. There is something strangely comforting about forces that never need to announce themselves. You cannot see them, you cannot hear them, you cannot touch them directly, and yet they are there, quietly shaping the world around you every moment of every day. Tonight, as the noise of the day slowly fades into the background, it may be interesting to spend some time thinking about one of the most silent and mysterious features of our universe: magnets. Almost everyone has held a magnet at some point in life. Perhaps it was attached to a refrigerator door. Perhaps it was part of a toy, a tool, or a machine. Most of us learn early that magnets can attract certain metals. They pull, they cling, they seem to reach across empty space. But the deeper you look into magnets, the more remarkable they become. Because magnets are not simply objects. They are visible evidence of invisible patterns that exist throughout nature. And in many ways, magnets offer a gentle reminder that some of the most powerful influences in the universe are the ones we cannot see. Imagine holding a small magnet in your hand. It feels solid and ordinary. Its weight is unremarkable. Its appearance may not seem special at all, yet surrounding it is a magnetic field extending outward into space. An invisible structure fills the area around it. Nothing announces its presence. No glow appears around its edges. No sound emerges from it. But the field exists nonetheless. Scientists often represent magnetic fields with elegant curved lines. These lines are not physical objects. They are visual tools that help us understand how magnetic forces flow through space. And there is something almost peaceful about these patterns. They emerge naturally. They organize themselves. They curve smoothly from one pole to another, like rivers finding their way through a landscape, or gentle currents moving through an ocean. The remarkable thing is that magnetic fields never become tired. A simple magnet can maintain its field for years, sometimes decades, sometimes much longer, without batteries, without fuel, without effort. It simply exists, quietly expressing the natural arrangement of countless atoms within its structure. When you begin examining magnets more closely, you discover that their behavior starts at an incredibly small scale. Inside magnetic materials are tiny particles called electrons. Electrons possess a property known as spin. The word spin can be slightly misleading because electrons are not literally spinning like miniature planets. Instead, spin is a fundamental characteristic of nature itself, and somehow, this property creates tiny magnetic effects. Every electron behaves like a microscopic magnet. Most of the time, these countless tiny magnetic influences point in random directions. When that happens, they cancel one another out. The material appears magnetically neutral. Nothing unusual seems to occur. But in certain materials, something beautiful happens. Large groups of atoms become aligned. Many tiny magnetic influences begin pointing in the same direction. Instead of canceling one another, they cooperate. Their effects combine. And from that collective order, a magnetic field emerges. There is something quietly fascinating about this idea. A magnet is not powerful because of one extraordinary particle. It is powerful because enormous numbers of tiny particles are working together. Order creates strength. Alignment creates influence. And perhaps that is one reason magnets feel strangely satisfying to think about. They transform microscopic organization into visible effects. The story of magnets stretches far back into human history. Long before scientists understood electrons or magnetic fields, people noticed unusual stones that seemed capable of attracting iron. These naturally occurring magnetic minerals were known as lodestones. Thousands of years ago, people encountered these stones with curiosity and wonder. Imagine discovering such a stone in an ancient world. You place a piece of iron nearby. The iron moves. No strings, no visible connection, no obvious explanation, only motion, only attraction. It must have seemed almost magical. Yet even then, the same physical principles were quietly operating. The same invisible fields, the same alignment of atoms, the same forces that continue to exist today. In a sense, every magnet you encounter is participating in a story that began billions of years ago, because the ingredients required for magnetism were forged deep within stars. The iron found on Earth originated through cosmic processes unfolding long before our planet existed. The atoms inside a simple refrigerator magnet have traveled an unimaginably long journey through space and time, and now they sit quietly in a kitchen, holding a note, supporting a photograph, performing their task without ceremony. One of the most calming aspects of magnetism is its consistency. Magnets do not choose when to work. They do not become distracted. They do not wake up one morning and decide to behave differently. The laws governing magnetic fields remain astonishingly reliable. If a magnet attracts a piece of iron today, it will do the same tomorrow and next year, and likely long after any individual observer is gone. There can be comfort in that kind of stability. The universe contains many complicated systems. Weather changes, ecosystems evolve, human societies transform constantly. Yet beneath all of this activity, fundamental forces continue operating with remarkable consistency. Magnetism is one of those quiet constants, a hidden rhythm woven into reality itself, and perhaps that is why magnets feel so satisfying to contemplate. They reveal a universe that is not chaotic beneath the surface, a universe where invisible structures create order, where patterns persist, where countless particles cooperate according to elegant rules, and all around you right now. Magnetic fields continue their silent work inside your speakers, inside your computer, inside electric motors, inside scientific instruments, even within Earth itself. A vast magnetic field surrounds our planet, an invisible shield stretching far into space, a planetary magnet quietly protecting life from streams of charged particles arriving from the sun. Most people rarely think about this shield, yet every moment of every day it remains there, unseen, dependable, patient. Oddimos eindbedi, waiting in the background like a silent guardian. And as we continue exploring the relaxing world of magnets, we begin to realize something unexpected. These simple objects are not merely tools. They are windows into a hidden layer of reality, a layer where invisible forces connect distant objects, where microscopic particles create macroscopic effects, and where order quietly emerges from countless tiny interactions. The more closely you look, the more magnetism begins to feel less like a scientific curiosity, a reminder that not everything important needs to be visible. Some of the most influential things in existence work quietly, continuously, and almost completely unnoticed. If you continue following the story of magnetism, your attention eventually arrives at one of the largest magnets you will ever encounter, the Earth itself. It may not feel like a giant magnet beneath your feet. The ground seems stable and motionless. Mountains appear permanent. Oceans seem to rest within familiar boundaries, yet hidden deep beneath the surface, far below the continents and seas, enormous movements are taking place. At the center of our planet lies a solid inner core surrounded by a vast layer of molten iron and nickel. This liquid metal is constantly moving, slowly, relentlessly, over immense spans of time. As these electrically conductive materials circulate, they generate magnetic fields. Together, these motions create what scientists call the geodynamo, and from this process emerges Earth's magnetic field. It is a remarkable idea. The entire planet is surrounded by an invisible magnetic structure extending tens of thousands of miles into space. You cannot see it from your window. You cannot feel it passing through your room. Yet it stretches far beyond the atmosphere, forming a protective bubble around the world. This magnetic shield helps deflect many charged particles arriving from the sun. Without it, life on Earth might have developed very differently. The planet's magnetic field is not rigid or frozen. It shifts gradually. It drifts. It changes shape over time. The magnetic North Pole itself slowly moves across the Arctic. For centuries, navigators have relied upon compasses that align with Earth's magnetic field. A simple compass contains a small magnet free to rotate. When left undisturbed, it naturally points toward magnetic north. There is something deeply elegant about this, a tiny piece of metal aligning itself with a force generated by the entire planet. No batteries, no software, no network connection. Just a quiet conversation between two magnetic fields. For hundreds of years, explorers crossed oceans using this invisible guidance system, long before satellites orbited overhead, long before digital maps appeared on glowing screens. A small magnetic needle helped people navigate vast stretches of uncertainty. Perhaps there is a broader lesson hidden there. Sometimes direction comes from forces we cannot see directly. Not everything useful announces itself loudly. Some guidance is subtle. Some influences operate quietly beneath the surface. Magnetism often works that way. One of the most fascinating chapters in the story of Earth's magnetic field involves creatures that seem able to sense it. Scientists have discovered evidence suggesting that many animals can detect magnetic information from their environment. Birds are among the most famous examples. Certain migratory species travel thousands of miles during seasonal journeys. They cross continents. They traverse oceans. They often return to remarkably precise locations. How they accomplish this has puzzled researchers for generations. The answer appears to involve multiple navigation systems working together. Among them may be an ability to perceive aspects of Earth's magnetic field. Imagine that for a moment. Imagine possessing a sense that most humans do not consciously experience, a subtle awareness of planetary magnetism, an invisible map surrounding the world. Some sea turtles appear capable of using magnetic information during long migrations. Certain fish may rely upon it. Even some insects show evidence of magnetic sensitivity. The more scientists investigate, the more they discover that Earth's magnetic field may serve as a kind of background reference system for many forms of life. It is quietly present, constantly available, a planetary signal woven into the environment, and most humans move through life almost entirely unaware of it. This is one of the recurring themes of magnetism: hidden layers, invisible structures, powerful influences that operate beyond ordinary perception. The universe is filled with them. Perhaps that is part of what makes studying magnets feel strangely calming. They remind us that reality is deeper than appearances suggest. There is always more happening beneath the surface. Another beautiful example appears in the night sky. Occasionally, charged particles from the sun stream toward Earth and interact with the planet's magnetic field. Most are redirected harmlessly away, but some become trapped and guided toward the polar regions. There, they collide with atoms in the upper atmosphere. The result is one of nature's most breathtaking displays: the aurora, soft curtains of green, waves of purple, shimmering ribbons of light. The northern and southern lights are, in part, visible expressions of invisible magnetism. Without Earth's magnetic field, these graceful displays would not exist in the same way. The lights seem almost dreamlike. Yet behind their beauty lies a story of magnetic forces stretching across space. The sun releases energetic particles. Earth's magnetic field guides them. Atoms respond. Light emerges. Invisible interactions become visible art. There is something profoundly satisfying about that transformation, a hidden process revealing itself through beauty. Magnetism also plays a central role in many technologies that quietly shape modern life. Consider the speakers that fill a room with music. Inside them are magnets. When electrical currents move through coils of wire, magnetic forces cause components to vibrate. Those vibrations create sound waves. Every song, every audiobook, every whispered voice through a speaker relies, in part, upon magnetism. The same is true for many electric motors, fans, appliances, industrial machinery, transportation systems. Magnets convert electrical energy into motion with remarkable efficiency. Much of the modern world moves because magnetic fields are interacting in carefully designed ways. Yet most people rarely think about these invisible processes. The machine appears to function almost effortlessly. The hidden magnetic dance remains out of sight. This invisibility gives magnetism a unique character. Gravity is familiar because we constantly feel its effects. Light is familiar because we constantly see it. But magnetism often operates quietly behind the scenes. It reveals itself indirectly, through movement, through alignment, through subtle influence. And perhaps that hidden nature is part of its appeal. The unseen can inspire curiosity in ways that visible things sometimes cannot. The mind naturally wonders about what lies beyond immediate perception. Magnetism invites that kind of wonder. It encourages a slower form of attention, a willingness to think about structures that exist whether or not we notice them. Even at the atomic level, magnetism continues revealing surprises. Quantum mechanics, the branch of physics describing the smallest scales of reality, shows that magnetism is deeply connected to some of the most fundamental properties of matter. The magnetic behavior of electrons arises from principles that challenge ordinary intuition. Particles behave in ways that seem almost impossible from a purely everyday perspective. Yet these strange quantum rules consistently produce the magnetic effects we observe. The refrigerator magnet, the compass needle, the electric motor, all are connected, ultimately, to microscopic phenomena occurring far beyond direct human experience. And still, despite this complexity, magnets often appear wonderfully simple. Place two magnets near each other. They attract or they repel. The behavior feels immediate and understandable. Beneath that simplicity lies an extraordinary depth of physics. But on the surface, the interaction remains almost soothingly straightforward. Push together, pull apart, approach, align, respond, a quiet choreography governed by natural laws. The more time you spend thinking about magnets, the more they seem to embody a certain balance between mystery and order. They are familiar enough to understand, yet deep enough to remain endlessly interesting. Simple enough for a child to explore, complex enough to occupy generations of scientists. And throughout all of it, magnetism continues its silent work. Invisible fields extending through space, particles aligning, forces interacting, patterns emerging. The universe, it seems, is filled with structures that do not demand attention. They simply exist, patiently, consistently, waiting for curious minds to notice them. As the story of magnetism continues, it becomes clear that magnets are not merely features of Earth. They belong to a much larger story, a cosmic story, one that stretches beyond our planet, beyond our solar system, and deep into the structure of the universe itself. When astronomers observe the sun, they are not simply looking at a giant ball of glowing gas. They are observing an immense magnetic machine. The sun possesses magnetic fields of extraordinary complexity. These fields twist, bend, and evolve over time. Unlike the relatively stable magnetic field surrounding Earth, the sun's magnetic environment is constantly changing. Loops of magnetized plasma can rise high above the solar surface. Some stretch for hundreds of thousands of miles. Others suddenly reconnect and release tremendous amounts of energy. These events can produce solar flares and vast eruptions known as coronal mass ejections. Despite their immense scale, they are driven by the same fundamental principles that govern a simple magnet on a refrigerator door. That is one of the most remarkable aspects of science. The same rules can operate across vastly different scales. The laws shaping a small magnetic object in your hand also help explain activity on a star more than 90 million miles away. The universe often displays this kind of quiet consistency. Patterns repeat, principles echo across distance and time, and magnetism is one of the threads connecting these different layers of reality. In fact, magnetic fields appear throughout the cosmos. Planets generate them. Stars generate them. Galaxies possess them. Even the space between stars contains magnetic influences. Astronomers have detected enormous magnetic structures stretching across regions of space so vast that they are difficult to imagine. These fields are invisible. No telescope can photograph magnetism directly. Instead, scientists observe its effects. They watch charged particles move. They study radio signals. They analyze patterns of light. From these clues, they reconstruct the hidden magnetic architecture of the universe. It is almost like discovering the shape of the wind by watching leaves move through a forest. The force itself remains unseen, but its influence becomes visible through everything it touches. There is something deeply calming about realizing how much of reality operates this way. Not everything important is immediately obvious. Not everything meaningful announces its presence. Many of the forces shaping the world work quietly in the background. Magnetism is one of nature's gentlest reminders of this truth. If you travel back to Earth and return to everyday life, you can begin noticing magnets in places that once seemed ordinary. The door of a refrigerator closes because of magnetic strips hidden within its seal. Credit cards and identification badges have often relied on magnetic storage. Headphones contain magnets. Microphones contain magnets. Many household appliances depend on magnetic components. Even large transportation systems frequently rely on magnetic principles. The modern world is filled with invisible magnetic relationships. Most of the time, These systems function so smoothly that they disappear into the background of awareness. We stop noticing them, yet they remain there, quietly supporting daily life. Perhaps familiarity is one reason magnetism can feel relaxing to contemplate. It is both mysterious and betemporal, strange enough to inspire curiosity, reliable enough to inspire trust. The force behaves according to clear principles. It does not surprise us with sudden unpredictability. A magnet attracts certain materials, repels another magnet under specific conditions, aligns with a magnetic field again and again, year after year. There is comfort in such consistency. Scientists have spent centuries studying magnetism, and despite all they have learned, questions still remain. Modern physics provides extraordinarily successful descriptions of magnetic behavior. Engineers can design complex technologies using magnetic principles with remarkable precision. Yet when researchers explore the deepest foundations of reality, mysteries still emerge. The universe often works this way. Each answer opens the door to new questions. Knowledge expands. Wonder expands with it. Magnetism is not a puzzle that has been completely solved and placed on a shelf. It remains an active area of exploration. Researchers continue investigating exotic magnetic materials. They study unusual quantum effects. They develop technologies that rely on increasingly sophisticated control of magnetic forces. Even now, laboratories around the world are uncovering new insights, and there is something reassuring about that. The pursuit of understanding continues. Curiosity remains alive. The story is not finished. One particularly fascinating area of research involves materials with unusual magnetic properties. Some substances behave in ways that challenge expectations. Certain materials become superconductors under special conditions. In these states, electricity can flow with extraordinarily little resistance. Magnetic effects in such materials can appear almost magical. Magnets can seem to float. Objects can levitate. The demonstrations are often striking. Yet behind the visual spectacle lies a deeper lesson. Nature is capable of behaviors far richer than our everyday experiences might suggest. The world is not limited to what appears obvious. Beneath ordinary appearances lie layers of complexity waiting to be discovered. Magnets reveal this repeatedly. The closer you look, the deeper the story becomes. Another intriguing fact is that magnetism and electricity are fundamentally connected. For a long time, scientists studied them separately. They appeared to be different phenomena. But during the 19th century, researchers gradually uncovered a profound relationship between them. Moving electric charges create magnetic fields. Changing magnetic fields can generate electric currents. The two are inseparable aspects of a larger phenomenon known as electromagnetism. This realization transformed science. Suddenly, many seemingly unrelated observations became part of a single framework. The universe revealed another layer of hidden unity. What appeared separate was actually connected, and perhaps that idea carries a quiet philosophical beauty. The natural world often contains connections that are not immediately visible. Separate events turn out to share common causes. Different systems reveal deeper relationships. Patterns emerge where none were previously noticed. Magnetism teaches this lesson repeatedly. What first appears simple gradually reveals complexity. What seems isolated often turns out to be connected. As the evening grows quieter, it is worth pausing for a moment to appreciate how extraordinary it is that invisible forces can shape so much of existence. A magnetic field has no color, no scent, no texture, yet it can guide migrating animals across oceans, protect an entire planet from harmful particles, power machines, store information, create sound, and help reveal the structure of the cosmos, all without ever becoming visible itself. Perhaps that is why magnets have fascinated humanity for so long. They occupy a unique place between the familiar and the mysterious. They are common enough to encounter every day, yet profound enough to inspire scientific investigation across centuries. A child can enjoy experimenting with magnets on a table. A physicist can devote an entire career to understanding them, and both are exploring the same fundamental force. There is something wonderfully democratic about that. Magnetism belongs to everyone. It exists around all of us, not hidden in distant laboratories alone, not confined to textbooks, but woven quietly into ordinary life. The magnet on a refrigerator, the compass in a backpack, the speaker beside a bed, the invisible field surrounding Earth itself. All are chapters of the same story. A story about order emerging from unseen interactions. A story about forces acting across empty space. A story about patterns that persist whether we notice them or not. And perhaps as your thoughts drift gently through these ideas, the world may feel just a little larger, a little deeper, a little more connected. Because everywhere around you, even now, invisible magnetic fields continue their silent work. Patient, steady, unhurried, existing as they always have. A quiet presence woven into the fabric of reality itself. If you spend enough time thinking about magnets, you eventually arrive at a curious realization. Magnetism is one of the few forces that most people encounter regularly, yet rarely stop to consider deeply. A magnet might sit on a refrigerator door for years. It becomes part of the background, almost invisible through familiarity. And yet, if someone from 1,000 years ago suddenly appeared in a modern kitchen, they might find that simple object astonishing. A piece of metal hanging against a vertical surface, defying expectations, holding papers in place through an invisible force. The extraordinary often becomes ordinary simply because it is familiar. Magnets remind us of this. They invite us to look again at things we think we already understand. And when we do, hidden layers begin to appear. Consider for a moment what happens when two magnets approach one another. At first, nothing seems to occur. The gap between them contains only air. No visible connection exists. Yet as the distance decreases, an invisible conversation begins. The magnetic fields overlap. The forces strengthen. Eventually, attraction or repulsion becomes noticeable. The magnets respond to each other across empty space. To the human mind, this can still feel slightly mysterious. After all, everyday intuition often expects contact before influence. We imagine one object pushing another, one thing touching another. Magnetism quietly challenges that assumption. It demonstrates that influence can travel through space itself. This idea once puzzled some of the greatest scientific thinkers. Even the brilliant physicist Isaac Newton expressed discomfort with the notion of forces acting across empty space without a visible mechanism. Yet nature seemed perfectly comfortable with it. The universe did not require physical contact to create effects. Magnetic fields carried information and influence naturally. Today, scientists understand these interactions far better than they did centuries ago. But the sense of wonder remains, because the deeper we explore, the more remarkable reality becomes. One especially fascinating feature of magnetism is that it creates patterns. If iron filings are scattered around a magnet, they arrange themselves into graceful curves. The filings act like tiny indicators, revealing the structure of the magnetic field. Suddenly, something invisible becomes visible. Order emerges from apparent randomness. The resulting shapes often look almost artistic. Smooth arcs spread outward. Elegant loops connect one pole to another. The patterns seem less like mechanical diagrams and more like natural works of design. There is a reason humans often find such structures calming. Our minds are drawn to patterns. We seek order. We look for relationships between things. When we encounter organized structures, especially ones that emerge naturally, they can create a subtle sense of satisfaction. Magnetic fields offer exactly that experience. They transform invisible complexity into understandable form. And perhaps that is one reason so many people enjoy watching demonstrations involving magnets. The interactions feel both surprising and orderly at the same time. The outcome follows clear rules. Yet there is still room for curiosity, still room for wonder. Nature often seems to strike this balance beautifully. Enough order to create stability, enough mystery to inspire exploration. The history of scientific discovery is filled with moments when magnets played an important role. During the 19th century, researchers began uncovering the deep relationship between electricity and magnetism. Experiments revealed that electric currents could create magnetic fields. This was an astonishing realization. Electricity and magnetism were not separate stories. They were connected chapters of the same narrative. One famous experiment involved a simple observation. A compass needle, normally aligned with Earth's magnetic field, moved when placed near a wire carrying an electric current. At first glance, the effect seemed small, but its implications were enormous. It revealed a hidden connection between two fundamental aspects of nature. From that point forward, science began weaving together ideas that had previously seemed unrelated. The result was one of the most successful theories ever developed: electromagnetism. This framework helped explain countless phenomena. It eventually led to technologies that transformed civilization: power grids, communication systems, computers, medical devices, and much more. All emerged, in part, from understanding the relationship between electricity and magnetism. Yet despite these extraordinary achievements, the underlying principles remain elegantly simple. Moving electric charges create magnetic effects. Magnetic changes can generate electricity. A beautiful exchange exists between the two, a kind of partnership woven into the structure of reality. Another calming aspect of magnetism is the way it reveals connections across different scales. A tiny magnet on a desk follows the same fundamental principles as Earth's magnetic field. The same laws helping a compass point north also help shape cosmic phenomena. The universe often operates this way. Small things and large things are linked by common rules. Patterns repeat across enormous ranges of size and distance. This consistency gives science much of its power. When researchers understand a principle in one context, they can often apply it elsewhere. A force discovered in a laboratory may help explain behavior occurring millions of miles away. Magnetism provides countless examples of this remarkable unity. In some sense, every magnet is a reminder that the universe is interconnected. The same physical laws apply whether you are examining a metal object on a table or observing activity on a distant star. The details may differ, the scale may change dramatically, but the underlying principles remain. There is something reassuring about that, a sense that reality possesses coherence, that beneath the complexity of the world lies a framework of enduring patterns. As researchers developed increasingly powerful instruments, they discovered that magnetic fields could also help reveal hidden information. One example appears in medical imaging. Certain scanning technologies use powerful magnetic fields to examine structures inside the human body, without surgery, without opening anything. Magnetism allows scientists and doctors to gather extraordinary amounts of information. Once again, invisible forces become tools for understanding. A magnetic field itself cannot be seen, yet it helps reveal things that would otherwise remain hidden. This seems to be a recurring theme. Magnetism acts as a bridge between the visible and the invisible, between what we observe directly and what exists beyond ordinary perception. And perhaps that is one reason the subject feels so rich. It encourages a particular kind of thinking, a willingness to look beneath appearances, to consider deeper structures, to imagine processes unfolding quietly beyond immediate awareness. The longer you reflect on magnets, the more they begin to feel less like isolated objects and more like expressions of a broader principle. Nature is full of relationships, fields, connections, interactions. Much of reality consists not simply of things, but of influences between things. Magnets make those relationships easier to see. They give form to invisible interactions. They allow abstract ideas to become tangible. And in doing so, they offer a gentle lesson about the world itself. Not everything meaningful is visible. Not every influence can be touched. Some of the most important structures exist quietly in the background, working continuously, shaping outcomes, guiding events, remaining largely unnoticed. As night deepens and thoughts begin to wander more slowly, magnetism starts to feel almost symbolic, an invisible force creating order, a hidden structure connecting distant points, a quiet influence operating without recognition. The magnets themselves ask for no attention. They simply continue doing what they have always done, generating fields, aligning particles, following the laws of nature with patient consistency. And perhaps there is something comforting in that image, a universe filled with silent patterns, countless invisible processes unfolding with steady reliability, a reality more organized, more connected, and more harmonious than it may first appear. All around you, at this very moment, those magnetic fields remain unseen, unhurried, endlessly patient. A quiet reminder that some of the most remarkable things in existence never need to announce themselves at all. As our exploration of magnetism continues, it is worth slowing down even further and considering a question that has fascinated scientists for generations. Why does magnetism exist at all? It is one thing to describe how magnets behave. It is another thing entirely to ask why nature allows such behavior in the first place. This is where the story begins to move towards some of the deepest ideas in physics. At the smallest scales known to science, the universe does not always behave according to everyday intuition. Objects are no longer simply objects. Particles are no longer tiny versions of familiar things. Instead, reality becomes stranger, more subtle, and in many ways, more beautiful. Electrons, which play a central role in magnetism, belong to this hidden world. They possess properties that have no perfect equivalent in ordinary life. One of those properties is what physicists call spin. The word itself sounds simple, yet it represents something remarkably profound. Spin is not merely motion. It is a fundamental characteristic of matter, a built-in feature of existence itself, and from this property emerges much of the magnetism we observe throughout the universe. Imagine that for a moment. The magnetic field around a refrigerator magnet, the magnetic shield surrounding Earth, the magnetic storms on the sun, all are connected, in some way, to the behavior of tiny particles possessing intrinsic properties that seem woven into reality from the beginning. There is a quiet elegance in this idea, enormous phenomena arising from tiny foundations, great structures emerging from simple rules. Nature often works this way. Complexity grows from simplicity. Vast systems emerge from countless small interactions. A forest emerges from individual trees. An ocean emerges from individual droplets, and magnetic fields emerge from unimaginable numbers of microscopic particles acting together. This pattern appears again and again throughout science. The whole becomes more than the sum of its parts. Magnets provide one of the clearest examples. No single atom creates the familiar strength of a household magnet. Instead, millions upon millions of atoms cooperate. Their tiny magnetic influences align. Their effects reinforce one another. Order accumulates. Strength emerges. The resulting field extends outward into space, invisible, persistent, calmly present. There is something almost meditative about observing how nature builds complexity through cooperation. The smallest components follow simple rules, yet together they produce phenomena of remarkable beauty. Perhaps this is one reason scientific ideas can feel soothing. They reveal a world where complexity is not necessarily chaotic. It often arises from deep underlying order. Magnetism also teaches an interesting lesson about balance. Every magnet has two poles, north and south. You can cut a magnet in half, then cut it again and again, yet each piece still forms its own north and south poles. Scientists have searched for isolated magnetic poles, known as magnetic monopoles, but none have been conclusively observed in nature. As far as current evidence suggests, magnetism prefers partnership. The poles remain linked. A complete magnetic field contains both. There is something quietly fascinating about that. Nature often seems to favor relationships rather than isolation. Many processes depend upon interactions. Opposites create structure. Differences generate movement. Connections produce stability. Magnetism reflects this tendency beautifully. Another remarkable feature of magnetic fields is their ability to store energy. Whenever magnetic fields form, energy becomes organized within space itself. This may sound surprising. After all, empty space often seems empty. Yet physics repeatedly reveals that space is far more active than appearances suggest. Fields exist within it. Energy moves through it. Information travels across it. Magnetic fields are part of this hidden activity. They occupy regions around magnets and electrical currents. Though invisible, they possess measurable properties. They can influence matter, transfer energy, create motion, and perform work. The more scientists study the universe, the more they discover that empty space is not truly empty at all. Instead, it serves as a stage upon which countless invisible processes unfold. Magnetism is one of the easiest ways to glimpse this reality. Place two magnets near one another, and the invisible becomes obvious. The fields interact, the magnets respond. Something unseen reveals its presence. In many ways, magnets act as ambassadors from a hidden world. They provide evidence that reality extends beyond direct sensory experience. This realization has played an important role in scientific progress. Again and again, humanity has discovered that important aspects of nature cannot be observed directly. Atoms cannot be seen with the naked eye. Radio waves cannot be seen. Gravity itself remains invisible, yet their effects reveal their existence. Magnetism belongs to this family of hidden influences, and because it can be demonstrated so easily, it offers a gentle introduction to a much broader truth. Reality contains more than appearances alone. There are structures beneath the surface, patterns behind events, invisible relationships shaping visible outcomes. As the years pass, scientists continue discovering new ways to use magnetic principles. Some of the most advanced technologies of the modern world depend upon precise control of magnetic fields. Researchers manipulate magnetic properties at scales smaller than a grain of dust. Engineers design materials with carefully tailored magnetic behaviors. Entire fields of study continue expanding from these efforts. Yet despite this sophistication, the basic wonder remains unchanged. A magnet still attracts a paperclip. A compass still points north. A magnetic field still extends silently into space. The same sense of curiosity that inspired ancient observers remains available today. That continuity is strangely comforting. Thousands of years separate modern scientists from the people who first encountered lodestones. Civilizations have risen and fallen. Languages have changed. Technologies have transformed beyond recognition. Yet the fundamental behavior of magnetism remains. The force that puzzled ancient thinkers is the same force studied in modern laboratories. Nature has remained remarkably consistent. The universe does not reinvent its laws every century. Its principles endure, and perhaps there is reassurance in that stability. In a world that often feels filled with constant change, some things remain reliable. Magnetism is one of them, a quiet thread connecting past and present, a reminder that beneath human history lies a deeper framework, a framework that existed before us and will continue long after us. As thoughts drift gently through these ideas, magnetism begins to feel less like a scientific topic and more like a lens through which to view the world. Invisible forces matter. Hidden structures shape outcomes. Small things working together can create extraordinary effects. Order often exists beneath apparent complexity, and reality is richer than immediate appearances suggest. These are lessons that magnets teach quietly, without speeches, without announcements, simply through their existence. The magnet never explains itself. It never demands attention. It simply demonstrates. A field extends outward. A force appears. An interaction occurs. And from those simple observations, entire worlds of understanding unfold. Perhaps that is the most relaxing aspect of magnetism. It does not overwhelm the mind. It invites it, gently, patiently, one observation leading naturally to another, one question opening the door to the next, until eventually you find yourself contemplating not merely a magnet, but the hidden architecture of reality itself. And all the while, the magnetic fields continue their silent work, surrounding the Earth, flowing through technology, shaping distant stars, connecting scales from the microscopic to the cosmic, invisible companions to the unfolding story of the universe. Steady, reliable, endlessly present, a quiet force woven through existence, asking for nothing, yet revealing so much. As we move deeper into the idea of magnetism, something subtle begins to shift in perspective. At first, magnets seem like simple objects with predictable behavior, attraction, repulsion, a force that is easy to demonstrate and easy to observe. But the more the mind lingers on them, the more they begin to feel like a doorway into something far broader. Not just a property of metal or stone, but a fundamental way the universe communicates with itself. One of the most intriguing aspects of magnetic fields is that they do not exist in isolation. They are always part of a larger system. A magnet is never truly alone in its influence. Its field reaches outward, interacting with everything in its environment. And those interactions are not static. They respond, they shift, they reshape each other. In physics, this is often described as fields interacting in space, but in a quieter sense, It can also be understood as a continuous conversation between regions of reality, a conversation without words, without sound, only structure and response. When you place a magnet near a piece of iron, something subtle happens before anything visible moves. The electrons inside the iron begin to reorient. Tiny magnetic domains shift alignment. The material is gently reorganized from within. This happens without noise, without effort, without delay that we can perceive. It is an immediate response at a scale far smaller than human awareness, and yet the result is something we can clearly see: movement, pull, contact. This layered behavior is one of the most interesting aspects of magnetism. What appears simple on the surface is supported by invisible complexity beneath. A visible effect emerges from an unseen structure, and that structure is constantly active, even when nothing is moving, even when nothing seems to be happening. Magnetic fields remain present, holding their shape, ready to respond to change. There is a quiet patience in that, a sense that the system is always listening, even when nothing is being asked of it. This idea becomes even more expansive when we step beyond individual magnets and consider entire environments shaped by magnetic forces. Inside planets, inside stars, inside galaxies, magnetic fields are not small details. They are structural elements. They influence motion on massive scales. They guide charged particles across enormous distances. They shape the paths of matter itself. In astrophysics, scientists observe that magnetic fields can organize streams of plasma in space, forming long, flowing structures that stretch for light years. These structures do not behave like rigid objects. They behave more like currents in an invisible ocean, slow, fluid, responsive to forces both near and distant. And yet, despite their scale, they are governed by the same fundamental principles that govern a simple magnet on Earth. This repetition across scales is one of the quiet signatures of nature. The same rules appear again and again, not as repetition of form, but repetition of principle. It suggests a kind of underlying consistency to reality, a stability that persists even as complexity grows. Back on Earth, magnetism also plays a role in ways that are less dramatic but equally constant. Inside electronic devices, magnetic fields guide the movement of data and energy. Hard drives, in earlier forms of computing, stored information using magnetic patterns. Even today, magnetism remains essential in many components of modern technology. It is part of the invisible infrastructure of daily life, not often noticed, rarely thought about, but constantly active. Every time a device starts, stops, or transmits information, magnetic interactions are quietly involved somewhere in the process. And yet, there is no sensation of this happening, no direct awareness, only results. Another interesting feature of magnetism is how it connects to motion. Whenever a magnetic field changes, it can induce electrical currents. This relationship between change and response is one of the foundational ideas in electromagnetism. It means that magnetism is never truly static in a meaningful sense. Even when a field appears stable, it is part of a larger system where motion and change are always possible. This dynamic nature gives magnetism a kind of latent energy, a readiness, a potential for transformation, not unlike a calm surface of water that can still carry deep currents beneath it. When scientists study magnetic fields in controlled environments, they often observe patterns that feel almost rhythmic, field lines forming loops, forces balancing and rebalancing, systems seeking equilibrium. There is a tendency toward structure, but also toward motion, a balance between order and change. This balance is not forced. It emerges naturally from the interactions of particles and fields. It is not designed in the traditional sense. It simply arises from the rules of physics. And this brings us to a quieter reflection. If something as fundamental as magnetism can produce both stability and change at once, then perhaps this duality is not unusual in nature. Perhaps many systems in the universe carry both stillness and motion simultaneously. On Earth, the magnetic field itself is a perfect example. It is stable enough to guide navigation, yet dynamic enough to shift over time. It protects the planet while constantly evolving. It is not fixed, but it is not chaotic either. It exists in a state of long-term balance. This kind of stability within change appears across many natural systems, weather patterns, ocean currents, even biological systems. Magnetism may simply be one of the clearest physical expressions of this deeper principle. As we continue to reflect on magnets, it becomes clear that their importance is not only scientific but also perceptual. They change how we think about influence. They show that effects do not always require contact. That distance does not necessarily prevent interaction. That invisible structures can shape visible outcomes. These are not just facts about physics. They are quiet lessons about the nature of reality itself. And the longer one considers them, the more they begin to feel less like abstract science and more like a way of seeing, a way of noticing what is usually overlooked. Around you, at this very moment, countless magnetic interactions are occurring in the devices you use, in the planet beneath you, in the space around you. Most of them will never be directly perceived, and yet they are part of the structure of your environment, unseen, uninterrupted, continuously present. As this awareness settles in, it often leads not to urgency, but to stillness, a recognition that much of reality does not require attention in order to function. It simply continues, quietly maintaining its patterns. And perhaps that is the most gentle insight magnetism offers, that beneath the surface of everyday life, there exists a stable network of invisible processes, not demanding observation, not seeking recognition, just existing in a state of quiet continuity. And as the mind follows that idea, it becomes easier to imagine the world not as a collection of isolated objects, but as a connected field of influences, a space where everything is subtly linked, where nothing is entirely separate, where even the smallest interaction is part of a larger, ongoing structure. And in that perspective, magnetism is not just a force, it is a reminder, a quiet demonstration that the world is always doing more than it appears to be doing, even in stillness, even in silence, even in the moments when nothing seems to change at all. As this exploration of magnetism continues, there is a point where the subject begins to feel less like a collection of facts and more like a way of perceiving time itself, because magnetic fields do not rush, they do not hesitate, they do not experience urgency. They simply, in that sense, magnetism carries a kind of timeless quality. It does not announce beginnings or endings, it maintains continuity. And when you begin to think about it this way, magnetism stops feeling like something that happens and starts feeling like something that is, a constant condition woven into the structure of space, always present, always active in the background. Even when no obvious motion is occurring, magnetic fields are still part of the environment, quietly existing in equilibrium with everything around them. This is especially clear when considering how magnetic fields interact with stability. A stable magnetic field does not mean an inactive one. It means a balanced one. Forces are still present, interactions are still occurring, but they are arranged in such a way that no large visible change takes place. It is a kind of still movement, or perhaps more accurately, a structured stillness. This idea can feel strangely relatable when applied beyond physics. Many systems in nature and life itself operate in similar ways. Appearances of calm often contain underlying activity. Appearances of simplicity often rest upon complexity. Magnetism reflects this pattern in a particularly clear form, because even the simplest magnet contains an internal structure of immense microscopic activity, atoms interacting, electrons aligning, domains stabilizing, all of it happening continuously, even when the object appears completely still. There is a quiet depth in that realization. Stillness does not mean absence of movement. It often means harmony among movements too small or too balanced to notice. And as attention returns again to the Earth itself, this principle becomes even more apparent. The planet's magnetic field is not a static shield drawn around a sphere. It is a living structure, generated by motion deep within the Earth's interior. Molten metals circulate slowly in the outer core. These flows are driven by heat, pressure, and the gradual cooling of the planet over time. From this motion, electrical currents emerge, and from those currents, magnetic fields arise. It is a continuous process, not something that was created once and then left unchanged. It is still happening, right now, beneath every ocean, every continent, every city. That deep internal movement continues. The magnetic field is not separate from Earth's dynamics. It is an expression of them, a visible, invisible signature of what the planet is doing beneath its surface. And yet, from the human perspective, the effect is experienced more gently, as a quiet directional tendency, a subtle alignment, a background structure that helps orient movement across the globe. It is interesting how something so large can feel so soft in its influence. The magnetic field does not push or pull in a dramatic way at human scale. Instead, it provides a framework, a reference, a gentle guide that becomes noticeable only when we choose to observe it. In navigation, this has always been its most practical role. A compass does not force direction. It reveals alignment, it responds, it settles, and in doing so, it translates an invisible planetary structure into a simple, readable gesture. A needle pointing north, a direction emerging from stillness. There is something almost poetic in that transformation, from planetary motion to a quiet indication in a handheld instrument, from molten metal deep within the Earth to a gentle rotation on a pivot. The scale difference is immense, yet the result is simple and usable. This bridging of scales is one of magnetism's most consistent themes. It connects the microscopic to the planetary to the cosmic, and the cosmic back to the microscopic again. In astrophysical environments, magnetic fields help shape matter on scales that are difficult to fully imagine. Between stars, in vast regions of space filled with gas and plasma, magnetic structures influence how material moves and gathers. They can guide streams of particles along invisible paths. They can organize diffuse matter into elongated formations. They can even contribute to the birth of stars by shaping how clouds of gas collapse under gravity. Again, the same underlying principle appears. Motion and field and motion, a continuous exchange that shapes structure over time. And yet, despite this immense scale, the behavior remains rooted in the same fundamental interactions found in everyday materials. There is a consistency here that is quietly profound. Whether in a laboratory, a planet, or a galaxy, magnetic behavior follows recognizable patterns, not identical in appearance, but unified in principle. This consistency allows science to build understanding across boundaries of scale. It allows human minds to connect observations from vastly different contexts into a single coherent framework. And perhaps that is part of why magnetism feels so satisfying to reflect upon. It is not fragmented. It is connected. It is not isolated. It is relational. Even in technology, this relational nature becomes clear. Magnetic fields are often used not as standalone forces, but as mediators of transformation. They convert energy from one form into another. They guide movement. They encode information. They translate invisible electrical activity into physical motion, sound, or stored data. A speaker turns electrical signals into sound waves through magnetic interaction. A motor turns electrical energy into rotation. A transformer adjusts voltage levels through changing magnetic fields. In each case, magnetism acts as a bridge, a translator between different expressions of energy. This bridging quality mirrors its role in nature. From cosmic structures down to human-made devices, magnetism often appears where transformation is happening, where one state is becoming another, where change is being guided rather than random. And as attention gently returns to the more abstract side of this topic, there is another idea that quietly emerges. Magnetic fields are not objects in the traditional sense. They are descriptions of relationships. They describe how space behaves around moving charges and aligned materials. In this way, magnetism is less like a substance and more like a pattern that repeats wherever the conditions are right. This shifts the way we think about things. Not everything in the universe is a thing you can hold. Some aspects of reality are better understood as structures of interaction, as relationships expressed through consistent behavior. Magnetism belongs to that category. It is not something separate from space. It is something space does under certain conditions, and when those conditions are present, the pattern appears predictable, reliable, stable, yet always tied to the deeper motion of particles and energy beneath it. As this reflection continues, the boundary between simplicity and complexity begins to soften. A magnet is simple enough to explain in basic terms, yet deep enough to connect to quantum physics, planetary dynamics, and cosmic structure. It exists at the intersection of scales, at the meeting point between the familiar and the profound. And perhaps that is what makes it so endlessly reflective. You can return to it again and again, each time noticing something slightly different, each time recognizing a deeper layer, and still the core behavior remains the same. Attraction, repulsion, alignment, interaction. A quiet system expressing itself through consistent rules. As the thoughts begin to slow, it becomes easier to see magnetism not as a topic to be mastered, but as a presence to be observed, always there, always steady, always unfolding according to its own quiet logic. And even when everything else fades into stillness, that underlying structure remains, invisible, patient, and continuously part of the world you are already within. As the mind stays with magnetism a little longer, something subtle begins to happen. The subject stops feeling like an external topic being studied, and starts feeling more like a background structure that has always been present, not because it is new, but because attention has finally slowed enough to notice it. Magnetism does not change in order to be noticed. It simply becomes clearer when observation becomes quieter, and in that quietness, even familiar ideas begin to feel slightly different. A magnet is still a magnet. A field is still a field, but the sense of separation between object and environment begins to soften, because a magnetic field is never truly isolated around a single object. It extends, it overlaps, it interacts with everything nearby, even if those interactions are too small to feel directly. In this way, magnetism can be thought of less as something contained and more as something shared, a region of influence that naturally blends into other regions of influence. This blending is continuous. There are no sharp boundaries where a magnetic field suddenly begins or ends in a dramatic way. Instead, it gradually weakens with distance, dissolving into the larger background of space. This gentle fading creates a kind of softness in how magnetism behaves. It does not abruptly stop. It does not violently change. It transitions smoothly, quietly, and that smooth transition is part of what makes magnetic interactions feel so stable in nature. They are governed by continuity rather than sudden interruption. Even when two magnets repel each other, the effect does not appear instantaneously at a distance. It emerges as the fields begin to overlap more strongly, a gradual increase in interaction, a slow recognition of proximity. There is a rhythm to it that feels almost organic, not in a biological sense, but in the sense of gradual unfolding, step by step, change by change, without sharp breaks. When this perspective is extended further, magnetism begins to resemble a kind of spatial conversation, each region of field responding to the presence of another, not through words or signals, but through continuous adjustment of force and alignment. In physics, this is described mathematically, with equations and vector fields and precise definitions. But beneath the formal language, there is a simple idea. Influence is shared through space, and space responds accordingly. This idea becomes even more interesting when considered alongside the structure of matter itself. Everything that feels solid is not truly solid at the microscopic level, in the way everyday intuition suggests. Atoms are mostly empty space. Electrons occupy regions of probability rather than fixed positions. And within this mostly empty structure, magnetic behavior arises from subtle alignments and motions. So what feels like solid interaction between objects is, at a deeper level, an interaction between fields, not just surfaces touching, but structures overlapping, patterns interacting. And this gives magnetism a slightly different character compared to many everyday experiences. It is not about collision. It is about alignment. It is not about impact. It is about relationship. When two magnets move toward each other, they are not hitting in a simple mechanical sense. They are responding to the structure of each other's fields. They are adjusting to a shared environment of influence. This relational quality is one reason magnetism is so central in physics. It is not an isolated force acting in one direction. It is part of a broader framework in which forces arise from interactions between fields and particles. And when viewed in this way, magnetism becomes less like a special effect and more like a fundamental language, a language the universe uses to organize interactions across space. One of the most remarkable aspects of this language is its universality. The same principles apply whether one is looking at a small object on a desk or a vast region of space filled with charged particles. Scale changes everything about appearance, but not necessarily about principle. A magnetic field near a wire carrying current follows the same underlying rules as magnetic structures in astrophysical plasma. The expression differs, the environment differs, but the logic remains consistent, and this consistency allows understanding to travel across scale. It allows scientists to use small experiments to infer large behaviors, and large observations to inform small-scale theory. There is a kind of intellectual calm in that structure, a reassurance that knowledge is not fragmented, but connected. As attention shifts again toward Earth, the same continuity appears in a more tangible form. The planet's magnetic field interacts constantly with streams of charged particles from the Sun. Most of these particles are deflected. Some are guided toward polar regions, and in those regions, energy is released in the form of light, the auroras. These glowing patterns in the sky are not separate from magnetism. They are expressions of it, visible outcomes of invisible structure, a reminder that what cannot be seen can still produce beauty that can be seen. There is something quietly powerful about that idea, that invisibility does not mean absence, and that influence does not require visibility. In daily life, most interactions with magnetism remain unseen, yet they are constant, within devices, within infrastructure, within the planet itself. Magnetic fields are always present where conditions allow them to form, not demanding attention, not requiring acknowledgement, just operating according to the structure of physical law. And perhaps that is where the calmest reflection arises, not from the dramatic effects of magnetism, but from its continuity, its persistence, its steady presence across time and scale. Even when nothing appears to be happening, magnetic fields remain part of the environment, holding their structure, responding when needed, returning to balance when disturbed. There is a kind of patience in that behavior, a sense that change is always possible, but not always necessary, that systems can remain stable without becoming static, that motion and stillness are not opposites, but partners within a larger framework. As thoughts gradually slow, it becomes easier to see magnetism not as a topic confined to science, but as an example of something broader, a way that reality maintains coherence across distance and time, a way that structure persists without becoming rigid, a way that influence travels without noise. And in that perspective, even something as simple as a magnet on a surface becomes a quiet illustration of deeper order, a reminder that beneath visible life, beneath motion and change, there are continuous patterns holding everything together in subtle ways, unseen, unbroken, and always present in the background of experience itself. As the reflection on magnetism continues, there is a point where attention begins to drift away from individual examples and move toward something more general, not a single magnet, not a single field, but the idea of fields themselves as a way the universe organizes influence. Magnetism is one expression of that idea, but it is not alone. Electric fields, gravitational fields, quantum fields, all of them point toward a similar structure beneath reality, a structure where what matters most is not isolated objects, but relationships between regions of space. In this view, space is not empty in the way it once seemed in early scientific thinking. Instead, it is active, structured, full of potential interactions that become visible only under certain conditions. Magnetic fields are one of the clearest ways to observe this hidden structure because they respond so directly to motion and alignment. But even when nothing is visibly changing, the underlying framework remains in place, stable, yet flexible, defined yet responsive. This duality appears again and again in magnetic behavior. A field can remain steady over time, yet still respond instantly when a new influence enters its region. There is no delay in awareness, no pause before reaction. The system is continuously connected to its environment, and that continuous connection is part of what gives magnetism its unique character. It does not behave like a disconnected object acting on another object. It behaves like a shared space of influence, a space in which changes ripple naturally through structure. This idea becomes easier to feel when thinking about how magnetic materials respond internally. Inside a ferromagnetic material, The atoms are not randomly oriented in their magnetic behavior. They form domains, regions where many atomic magnetic moments align in the same direction. These domains can shift, expand, shrink, reorganize. When an external magnetic field is applied, the domains do not resist in a purely rigid way. They adjust. They respond to the new conditions. Over time, alignment becomes more coherent. The material becomes magnetized. What is important here is not just the final state, but the process itself, a gradual reorganization, a slow coordination of internal structure in response to external influence. There is a kind of collective behavior taking place at a scale too small to see directly, and yet its outcome is easily observed. This relationship between invisible process and visible result is one of the most consistent themes in magnetism. It is not the surface that matters most. It is the structure beneath the surface. As attention moves outward again, away from materials and toward larger systems, similar patterns appear. The Earth's magnetic field is not static. It shifts over time. It drifts across the surface of the planet in a phenomenon known as magnetic variation. Navigation systems must account for this slow movement, because the direction indicated by a compass is not fixed in a universal sense. It depends on the current state of Earth's magnetic structure. Even something as seemingly stable as north is actually part of a dynamic system, a reference that changes slowly, almost imperceptibly, across years and centuries. This introduces a subtle idea. Stability in nature is often long-term behavior rather than absolute permanence. Things can appear constant on a human timescale, while still changing gradually in the background. Magnetism embodies this perfectly. It is both steady and evolving, reliable and dynamic, predictable in the short term, yet fluid in the long term. This combination allows it to serve as both a practical tool and a subject of deep scientific inquiry. In technology, magnetism often appears where transformation of energy is needed. Electric motors convert electrical energy into motion through magnetic interaction. Generators convert motion back into electrical energy. Transformers adjust voltage levels by manipulating magnetic coupling between coils. In each case, magnetism acts as a mediator, a bridge between different forms of energy, a mechanism through which change is guided rather than chaotic. There is a kind of elegance in this role. Magnetism does not create energy from nothing. It reorganizes it, redirects it, translates it from one form into another. This idea of translation, rather than creation or destruction, is important in physics. It reflects a broader principle of conservation and transformation. Energy changes form, but the underlying total remains consistent within a closed system. Magnetic fields are one of the tools through which this transformation becomes practical and observable. At the same time, magnetism also connects deeply to information. In earlier technologies, magnetic storage was used to encode data in physical materials. Patterns of magnetization represented binary information. Modern systems have evolved beyond many of these methods, but the principle remains foundational. Information can be stored physically through alignment, through structure, through stable patterns in a magnetic medium. This introduces a more abstract idea that magnetism is not only about force or motion, it is also about organization, about how states are arranged and maintained over time. A magnetic domain aligned in one direction represents a kind of stored condition, a persistent state within a material. This persistence is what allows memory in physical systems, and in a broader sense, it highlights how physical laws can support informational structures. As reflection deepens further, it becomes clear that magnetism sits at an intersection of multiple concepts: force, energy, structure, information, space, time. It is not confined to a single category. Instead, it appears across many layers of description, and this multi-layered nature is part of what makes it so rich as a subject of thought. It resists reduction to a single intuitive image. Instead, it expands outward depending on how it is examined, from simple attraction between objects to the behavior of galaxies, from atomic alignment to planetary fields, from practical devices to cosmic structure. At every level, a similar pattern reappears. Interaction through fields, organization through alignment, response through influence, and underlying all of it is a sense of continuity. Magnetism does not appear as isolated events. It appears as ongoing conditions, always present when the right circumstances exist, always ready to respond, always part of a larger system. As the mind gradually settles into this perspective, magnetism begins to feel less like a subject to be learned and more like a background feature of reality itself. Not something that begins or ends, but something that persists, quietly shaping interactions across scales too large and too small to fully perceive at once. And in that quiet persistence, there is a subtle kind of calm, a reminder that beneath the surface of change, there are structures that remain steady, not frozen, not rigid, but continuously maintained through balance and interaction, always present, always active, yet never demanding attention, just existing as part of the deeper fabric of the world. As we move even deeper into this quiet reflection on magnetism, the perspective begins to shift again, this time toward something more subtle than force or field, toward perception itself. Because magnetism, for all its physical presence in the universe, is not directly accessible to human senses. You do not see it, you do not hear it, you do not feel it in the way you feel heat or pressure, and yet it is constantly present, shaping motion and structure at every scale. This creates an interesting situation. A fundamental part of reality exists outside of direct perception, and yet its effects are everywhere. So what we call understanding magnetism is, in a sense, learning to interpret indirect signs. The movement of a compass needle, the behavior of iron filings, the response of materials in a field, the structure of auroras in the sky. Each of these is not magnetism itself, but evidence of it, traces of an invisible pattern made visible through interaction with matter. This distinction is important because it reveals something about how knowledge of the world is built. We rarely encounter fundamental forces directly. Instead, we encounter their expressions, and from those expressions, we infer structure. Magnetism becomes not just a physical phenomenon, but an example of how the human mind connects observation to underlying reality. There is a quiet elegance in this process, a steady movement from effect to cause, from visible change to invisible structure, from motion to field. And once this way of thinking becomes familiar, it begins to extend beyond physics, because much of life operates in similar layers. We often experience outcomes long before we understand their sources. We see patterns before we understand their origins. We notice stability or change without immediately perceiving what generates it. Magnetism simply makes this relationship more visible, because the connection between cause and effect is so clean, so structured, so consistent. A change in alignment produces a predictable response. A movement through a field produces a measurable effect. There is little ambiguity in the behavior, and that clarity gives magnetism a certain intellectual calmness. It does not rely on hidden exceptions or unpredictable behavior in ordinary conditions. It follows stable rules, and those rules scale smoothly from small systems to large ones. This brings us back again to the idea of fields as a universal language. Magnetism is one expression of that language, but it shares its grammar with other fundamental interactions. What changes is not the structure, but the context, the conditions under which the field becomes noticeable, the way it interacts with matter, the scale at which its effects become meaningful. In everyday life, magnetism often appears only when materials are arranged in specific ways. Iron, nickel, cobalt. Certain configurations allow magnetic interactions to become strong enough to observe directly. But the field itself does not depend on observation. It is always present wherever its conditions exist. This separation between existence and perception is one of the more quietly profound aspects of physics. Reality does not wait to be observed in order to function. It continues regardless of attention. Magnetic fields do not strengthen when studied, nor weaken when ignored. They simply persist according to their underlying rules. And yet, human understanding depends entirely on observation. This creates a relationship between the world and the mind that is inherently indirect. We do not access reality itself in raw form. We access signals, patterns, harness, effects, and through careful interpretation, we construct models that approximate the underlying structure. Magnetism has played an important role in refining this approach. Because its behavior is both observable and deeply consistent, it provides a reliable foundation for understanding invisible processes. Over time, this has led to increasingly precise descriptions of how magnetic fields behave, interact, and evolve. But even with mathematical precision, the underlying experience remains simple at the surface level. A magnet attracts a piece of metal, a compass points in a direction, a current generates a field influences motion. These interactions are consistent enough to feel almost gentle in their predictability. And perhaps that predictability is part of what makes magnetism so conducive to slow reflection. There is no sudden disruption in its behavior under normal conditions, no abrupt deviation from expected patterns. It behaves like a system that is continuously in conversation with itself, adjusting smoothly as conditions change. This continuity extends into larger natural systems as well. Earth's magnetic field, for example, does not fluctuate wildly in everyday timeframes. It shifts gradually. It responds to deep planetary processes that unfold over long periods. In this sense, magnetism reflects a broader principle seen throughout nature. Significant systems often change slowly. Stability is not the absence of change, but the result of balanced change over time. This perspective can subtly reshape how one thinks about motion and stillness. What appears still may simply be changing too slowly to notice. What appears active may be part of a stable long-term pattern. Magnetism exists comfortably within this duality. It is both active and stable, both changing and consistent, both simple in expression and complex in origin. And as attention continues to drift through these layers, the idea of magnetism as a thing becomes less central. Instead, it becomes easier to think of it as a behavior of space and matter under certain conditions, a pattern that emerges naturally, a structure that reveals itself when alignment and motion interact in specific ways. This shift in perspective removes the need to imagine magnetism as something separate from the world. It is not added to reality. It is part of how reality organizes itself. And once that idea settles in, even familiar objects begin to feel slightly different. A magnet is no longer just a tool or object. It is a localized expression of a broader principle, a small region where the structure of space reveals itself in a particular way. Around it, nothing is truly separate, only varying degrees of interaction, only fields overlapping and responding, only continuous adjustment across space. As the reflection gently continues, there is no final point of arrival. Magnetism does not resolve into a single simple idea. It remains layered. It remains expansive. It continues to unfold depending on how deeply it is considered. And perhaps that is part of its quiet appeal. It does not demand conclusion. It allows continuation, a steady presence in the background of thought, always present, always consistent, always quietly shaping the structure of the world, whether noticed or not. As this reflection continues, there is a gradual return to something even more fundamental than structure or force, a return to how magnetism relates to space itself. Because magnetic fields do not exist inside objects alone. They exist in space, in the regions between objects, in the invisible gaps that separate everything we can see. And this changes how space is understood. Space is no longer just an empty backdrop where events happen. It becomes an active participant in those events, a medium through which influence is distributed and organized. A magnet does not reach out across emptiness in a mechanical sense. It shapes the space around it, and that space, in turn, influences other objects within it. This mutual relationship is central to modern physics, but it also carries a more intuitive meaning when thought about slowly. Instead of objects acting directly on each other, space itself becomes the intermediary, a shared environment of influence. And magnetism is one of the clearest ways to observe this idea in action. When a magnetic field is visualized, it is often represented with smooth, continuous lines. These lines are not physical paths. They are representations of direction and strength. Yet they give the impression that space has structure, that it is not uniform, that different regions carry different tendencies. This is a powerful shift in perspective, because it suggests that what surrounds objects is not passive emptiness, but structured presence. Even if that structure cannot be seen directly, its effects can be measured, and those effects are consistent, predictable, reliable. As attention deepens into this idea, it becomes clear that magnetism is less about individual objects and more about the geometry of interaction, how space curves influence motion, how alignment creates direction, how gradients in field strength guide behavior. In this sense, magnetism is not simply a force applied from one point to another. It is a pattern distributed across regions of space, a pattern that determines how objects move within it. This distributed nature is what allows magnetic fields to act without contact. No pushing, no touching, no direct collision required. Only structure interacting with structure. And because this structure extends smoothly through space, its effects also appear smooth. Objects do not jump abruptly when entering a magnetic field. They respond gradually, as if moving through a gently sloping landscape rather than a sharp boundary. This analogy of landscape is often used in physics for good reason. Magnetic fields can be thought of as shaping a kind of invisible terrain, where different regions correspond to different levels of influence. Objects placed within this terrain respond to its shape. They move along gradients. They align with directions of least or greatest resistance, and this movement is not imposed. It emerges naturally from the structure itself. There is something deeply consistent in this behavior. No sudden discontinuities, no arbitrary changes, only continuous variation, as if the universe prefers smooth transitions over abrupt ones. This preference for continuity appears in many areas of physics, but magnetism expresses it in a particularly visible way, even when fields change. They do so through gradual evolution, through shifts in alignment and distribution, through reorganization of underlying structure rather than sudden replacement. This gives magnetism a kind of fluid character. Even though it is not a fluid in the traditional sense, it behaves as if it flows through space, even though what is flowing is not material substance but influence. This brings attention again to the idea of fields as real entities, not just mathematical tools, but descriptions of something physically meaningful. They encode how space behaves under certain conditions, and that behavior has measurable consequences. The distinction between object and field begins to blur here. Objects are no longer isolated points acting independently. They are regions where fields concentrate, overlap, and stabilize. A magnet is not separate from its field. It is a configuration of matter that produces a particular field structure, and that field structure extends beyond the object itself. In this way, every magnetic object participates in a larger spatial pattern, a pattern that does not stop at its surface, a pattern that blends into surrounding space. And this blending is continuous, not fragmented, not segmented, but smooth and ongoing. As reflection continues, it becomes natural to consider how this perspective changes the idea of boundaries in general. If magnetic fields do not have sharp edges, then the distinction between inside and outside becomes less absolute. Instead, there are degrees of influence, regions where a field is strong, regions where it weakens, regions where it fades into background conditions. This gradation replaces the idea of strict separation with one of continuous transition, and this concept, while originating in physics, often resonates more broadly, because many systems in nature also behave in gradual ways. Changes in weather, shifts in ecosystems, movements in populations. Rarely do these systems switch instantly from one state to another. They evolve slowly, continuously. Magnetism simply expresses this principle in a precise and consistent physical form. Another important aspect of magnetic fields is their responsiveness to motion. When charges move, magnetic fields emerge. When fields change, motion can be induced. This reciprocal relationship creates a dynamic system where cause and effect are intertwined, not linear in a simple sense, but circular in interaction. One influences the other, and the other feeds back into the first. This creates a loop of continuous adjustment, a system that is always in a state of interaction rather than separation. And yet, despite this complexity, the behavior remains governed by stable laws. This combination of dynamic interaction and stable rule is one of the defining features of electromagnetism as a whole. It allows for both predictability and flexibility within the same framework. As attention gently returns to the more reflective side of the subject, magnetism begins to feel less like a topic being examined and more like a pattern being noticed everywhere, not confined to laboratories or textbooks, but present in the structure of reality itself, in the way space organizes influence, in the way matter responds to fields, in the way systems maintain balance through continuous adjustment. And as this awareness deepens, there is no need for conclusion or resolution, because magnetism does not conclude. It continues, quietly, steadily, existing wherever the conditions for it exist, a constant presence in the background of the universe, unseen, uninterrupted, and always unfolding in place. As this long reflection continues, magnetism begins to feel less like a topic being extended, and more like a landscape that slowly unfolds as attention moves through it. Not something that is being added to, but something that was always already there, gradually becoming more visible as the mind lingers. At this point, it becomes useful to notice how magnetism interacts with motion itself, because motion is not separate from magnetic behavior. In many cases, motion is what gives rise to magnetism in the first place, and magnetism in turn can generate motion. This reciprocal relationship creates a continuous loop, a system where cause and effect are intertwined rather than strictly linear. When an electric charge moves, it generates a magnetic field around it. That field is not static. It forms a structured region of influence in space, and if that field changes, it can influence other charges nearby, causing them to move. So motion creates field. Field influences motion. Motion reshapes field again. A continuous cycle of interaction. There is something almost rhythmic in this structure when it is considered slowly, not a rhythm in time like music, but a rhythm in relationships, a pattern of response and adjustment. In physics, this is described mathematically with great precision, but in a quieter sense, it can also be understood as a form of ongoing balance. Nothing remains isolated. Everything is part of a connected system of influence. And magnetism is one of the clearest expressions of that connectivity. Even when nothing appears to be changing, this system remains active. Charges are still present. Fields are still defined. Space is still structured in specific ways depending on the distribution of matter and energy. There is no true pause in the underlying framework, only changes in how noticeable those interactions become. This leads to an interesting idea. Stillness is often not absence of activity, but equilibrium within activity, a balance of forces that results in no large-scale movement. In magnetism, this is especially evident. A magnetic field can be completely stable in appearance, while still representing continuous underlying structure. The atoms in a magnet are not frozen in place in a simplistic sense. They are part of an ongoing quantum system, governed by rules that maintain alignment over time. That alignment is not passive. It is sustained, held in place by energetic relationships between particles. So even stability has depth. It is not emptiness. It is maintained order, a kind of quiet persistence. As attention moves outward again, the same principle can be seen on much larger scales. The Earth's magnetic field, for example, is the result of continuous movement in the planet's molten outer core. Liquid iron and nickel flow in complex patterns driven by heat and rotation. These flows generate electrical currents. Those currents generate magnetic fields, and those fields feed back into the system, influencing motion within the core itself. This is not a simple one-directional process. It is dynamic, self-sustaining, continuously evolving. Yet, from the surface, the result appears stable, a consistent magnetic field surrounding the planet, a field that allows compasses to function, a field that helps guide navigation, a field that exists quietly, even as its internal source remains in constant motion. This contrast between internal dynamism and external stability is one of the most interesting features of natural systems. It appears in weather systems, in ocean currents, in biological systems, and in magnetic fields as well. Complex internal processes can produce stable external patterns. This suggests that stability does not necessarily mean simplicity. It can also emerge from complexity, when many interacting parts balance each other over time. Magnetism provides a clear example of this principle. Another layer of reflection appears when considering how magnetic fields are detected. They are not seen directly. They are inferred through interaction. A compass needle rotates. Iron filings align. Particles move in curved paths. Each of these effects is not the field itself, but a response to it. So understanding magnetism requires interpreting behavior rather than observing the field directly. This creates a subtle but important shift in how knowledge is constructed. It is not always about direct perception. It is about consistent inference from repeated outcomes. This method of understanding extends far beyond magnetism. It is one of the core approaches of science itself, but magnetism makes it especially clear because its effects are so consistent and reproducible. The same setup produces the same result over and over again, without deviation in normal conditions. This reliability gives magnetism a kind of intellectual clarity. It is a system where patterns can be trusted, where relationships remain stable across repeated observation, and in that stability, there is a quiet sense of order, not emotional order, not narrative order, but structural order, the kind that exists regardless of whether anyone is observing it. As reflection continues, magnetism also begins to appear as a kind of mediator between different forms of energy. It does not exist in isolation from electricity. It does not exist separately from motion. It connects them, transforms them, translates them. Electric energy can become motion through magnetic interaction. Motion can become electrical energy through magnetic induction. This conversion process is not accidental. It is built into the structure of physical law. And because of this, magnetism becomes a key mechanism through which energy changes form in the natural world. This transformation is not destructive. Nothing is lost in the process. At a fundamental level, energy shifts from one configuration to another, from electrical potential to mechanical movement, from movement back into electrical flow. Magnetism is part of this continuous exchange, a bridge across forms of expression. And as this idea settles in, it becomes easier to see magnetism not as a standalone force, but as part of a larger system of relationships, not something separate from the world, but something that helps define how the world behaves. It is woven into motion, into structure, into interaction itself. Even the idea of force begins to feel less like a push or pull in a simple sense, and more like a pattern of influence distributed through space, a pattern that shapes how matter behaves when conditions align. And because those conditions exist widely in nature, magnetism appears almost everywhere, in planets, in stars, in technology, in microscopic materials. It is not rare, it is foundational. As this long reflection gradually continues, there is no final conclusion emerging, no endpoint where magnetism is fully exhausted or fully contained. Instead, what remains is continuity, a sense that the subject extends beyond any single description, that each layer of understanding reveals another layer beneath it, and that beneath all layers, the same quiet structure remains present, fields interacting, matter responding, space organizing influence, and through it all, a stable yet dynamic system unfolding without interruption, always present, always active, always quietly shaping the structure of reality itself. As the exploration continues, magnetism begins to feel less like a subject being described and more like a principle that quietly underlies many of the patterns already discussed. At this stage, it becomes difficult to separate magnetism from the broader behavior of nature itself, because the same themes appear again and again: interaction, alignment, response, continuity, and perhaps most importantly, connection across distance without direct contact. This idea of connection without contact is one of the most quietly profound aspects of magnetic behavior. In everyday intuition, influence is often associated with touching. One object pushes another. One surface meets another surface. Change is expected to happen through direct interaction. But magnetism does not follow that limitation. It acts through space itself, not as emptiness, but as structured presence. A magnet does not need to touch an object in order to influence it. Its field extends outward, and within that field, other materials respond. This challenges a very basic assumption about how interaction works. It suggests that separation does not necessarily mean independence. Two objects can remain physically apart and still be deeply connected through the structure of the space between them. This concept becomes more intuitive when the idea of a field is held gently in mind. A field is not a line drawn between objects. It is a region of influence that fills space continuously. Every point within that region has a defined relationship to the source: strength, direction, orientation. These properties are not localized at a single point, but distributed across space. And so, when another object enters that region, it does not encounter emptiness. It encounters structure. This structure guides behavior. It shapes motion. It influences alignment. And it does so gradually, in proportion to distance and orientation. There is a kind of smoothness in this interaction that distinguishes it from more abrupt forms of contact. No sudden collision is required, no instant transition, only gradual response as conditions change. This smoothness is one reason magnetic phenomena often feel so stable in their behavior. They do not introduce discontinuities into motion under normal conditions. Instead, they gently modify trajectories. They adjust direction. They encourage alignment. Even the simplest demonstration of magnetism reflects this. A small piece of metal placed near a magnet does not instantly snap into position in a purely discontinuous sense. It accelerates. It responds. It transitions through space in a way that reflects the strength and shape of the field around it. The process is continuous, not abrupt, and this continuity mirrors a broader principle in physics. Many natural interactions favor smooth change over sudden jumps. When change occurs, it often unfolds gradually through intermediate states. Magnetism expresses this principle clearly and consistently. Another layer of understanding appears when considering that magnetic fields are not independent entities floating in space. They are generated by conditions within matter, moving charges, aligned spins, internal structure. This means that magnetism is deeply tied to the behavior of matter itself. It is not separate from the physical world. It emerges from it. This emergence is important. It means that magnetism is not something added to matter from outside. It is a consequence of how matter behaves under certain conditions. This shifts the way it is understood. Instead of thinking of magnetism as a force acting on matter from a distance, it becomes more accurate to think of it as a property arising from the state of matter and space together, a relationship rather than a thing, a pattern rather than an object. And once this shift is made, magnetism begins to feel less isolated. It becomes part of a broader network of physical principles where behavior emerges from interaction. This perspective also helps explain why magnetism appears in so many different contexts, because wherever the conditions are right, where charges move, where spins align, where structures organize, magnetic effects naturally arise, not as exceptions, but as expressions of underlying rules. This universality is one of the most striking features of physics in general, simple rules producing widespread and varied phenomena. Magnetism is one of the clearest examples of this principle. From the smallest atomic interactions to the largest cosmic structures, the same foundational behavior appears in different forms. The expression changes, the scale changes, but the underlying structure remains recognizable. This continuity across scale gives magnetism a kind of unifying role in physical understanding. It connects microscopic processes to macroscopic effects. It links the invisible world of particles to the visible world of objects and motion, and it does so without requiring fundamentally different rules at each level. Instead, the same rules express themselves in different contexts. As attention continues to rest on this idea, it becomes clear that magnetism is not only about forces or fields, but about relationships that persist across transformation. It describes how systems maintain structure while changing state, how alignment can emerge from motion, how stability can arise from interaction. Even in systems that appear chaotic at first glance, magnetic order can emerge when conditions allow. Particles align, fields form, patterns stabilize, and these patterns can persist over time even as the underlying components continue to move. This balance between motion and order is one of the most important aspects of magnetic systems. Nothing is truly static, yet nothing is entirely random either. There is structure within movement, and movement within structure. This duality allows magnetic systems to be both dynamic and stable at the same time. Another interesting aspect appears when considering how magnetic fields respond to changes in their environment. They do not exist in isolation. They interact with other fields, with materials, with motion. When a new influence is introduced, the existing field adjusts, it redistributes, it reorients, it rebalances. This responsiveness gives magnetism a kind of adaptive quality, not in a conscious sense, But in a structural sense, the system naturally evolves toward equilibrium under changing conditions, and this tendency toward balance is another recurring theme in physics. Systems often move toward states of lower energy or greater stability over time. Magnetism participates in this broader tendency. As interactions occur, configurations shift toward more stable arrangements, alignments become more consistent, opposing influences balance out, and the system settles into a configuration that reflects the surrounding conditions. But this settling is never permanent in an absolute sense. If conditions change again, the system responds again. Equilibrium is not a fixed point. It is a dynamic state maintained through continuous adjustment. This gives magnetism a quietly active character. Even in its most stable forms, there is always underlying potential for change, always readiness to respond. Even in stillness, there is structure waiting to shift. As reflection slowly continues, magnetism becomes less about individual phenomena and more about a way of understanding interaction itself, a way of seeing how influence travels, how structure emerges, how stability is maintained, and how change unfolds through continuous adjustment rather than abrupt transition. It is not a single idea. It is a framework that appears across many levels of reality. And as attention gently settles into this broader perspective, there is no need for resolution or conclusion, because magnetism does not conclude. It persists quietly, continuously, existing wherever conditions allow structure, motion, and alignment to meet, a steady presence in the background of reality, always unfolding, always connected, always part of the ongoing fabric of the world. As this long meditation on magnetism continues, there is a natural slowing of attention that begins to occur, not because the subject becomes less interesting, but because it becomes more complete in its repetition of patterns. The same principles appear again and again in different forms: fields, interaction, alignment, response, continuity. At some point, the mind starts to recognize that it is not moving forward in a linear sense anymore. It is circling through layers of the same underlying structure, each time seeing it from a slightly different angle, and that in itself reflects something important about magnetism. It is not a phenomenon defined by one direction or one moment. It is defined by relationships that persist over time. A magnetic field is not a snapshot. It is a continuous state of interaction, always present as long as conditions remain, and always ready to shift when those conditions change. This continuity is one of the most important qualities in understanding how magnetism behaves in the physical world. Nothing about it is truly isolated. Every magnetic effect is part of a larger system of interactions that extends beyond immediate perception. Even a simple magnet on a surface is not an independent object in a meaningful physical sense. It is embedded in a field that extends outward into space, a field that interacts with surrounding materials, a field that responds to changes in position, orientation, and environment. This embedding is subtle but constant, and it means that magnetism is never just inside or outside a single object. It is distributed across space in a continuous way. When this idea is held gently, it begins to change how separation itself is understood. The boundary between objects and environment becomes less rigid, less absolute. Instead, there are gradients of influence, regions where interaction is stronger, regions where it weakens, regions where it becomes negligible, but never truly disappears in a strict sense. This gradient structure is central to how magnetic fields are described mathematically, but it also has an intuitive quality when considered slowly. Nothing in the field changes suddenly at a sharp edge. Everything transitions smoothly, and this smoothness creates a kind of coherence across space, a continuity that allows influence to propagate without interruption. In physical terms, this is what allows magnetic effects to extend across distance. But in a more reflective sense, it also reveals something about how structure itself is distributed in nature. It is not always concentrated in single points. It is often spread across regions, shaped by relationships rather than isolated positions. As attention remains with this idea, magnetism begins to feel less like a force acting within space and more like a description of how space organizes interaction, a language for expressing how influence behaves when matter and motion are present. And this language is remarkably consistent. It does not change depending on scale. The same principles appear in small systems and large systems alike. At the atomic level, magnetic behavior arises from the motion and alignment of electrons. At the planetary level, it arises from fluid motion in conductive materials. At the stellar and galactic level, it emerges from plasma and large-scale currents. In each case, the underlying mechanism is different in detail, but similar in structure. Motion creates field. Field influences motion. Interaction produces organized behavior. This repetition across scale is not accidental. It reflects a deep consistency in how physical laws operate, and magnetism is one of the clearest demonstrations of that consistency. Another important aspect is how magnetism relates to direction. A magnetic field is not just a strength or intensity, it has orientation. It defines a direction at every point in space. This means that space is not only structured in terms of how strongly it influences matter, but also in terms of how that influence is directed. This directional quality gives magnetic fields a kind of geometry, not a static geometry like a solid shape, but a dynamic one defined by influence. Objects placed within this field do not simply feel a push or pull. They experience a directional tendency that varies depending on their position and orientation. This introduces a subtle complexity, because the behavior of a system depends not only on where it is, but how it is oriented within the field. This dependence on orientation adds depth to the interaction. It is not purely scalar. It is vectorial, structured in both magnitude and direction. And this structure allows for a rich range of behaviors, even in relatively simple systems. From a calm perspective, this can be seen as another expression of balance within complexity. Simple rules producing layered outcomes. Consistent principles generating varied behavior depending on context. Magnetism does not need to change its rules to produce different effects. It only requires different configurations, different alignments, different distributions of matter and motion. And from those variations, a wide range of phenomena can emerge. At the same time, magnetism remains fundamentally conservative in its behavior. It does not introduce randomness in ordinary conditions. It follows predictable patterns. This predictability is what makes it useful in technology. It allows engineers and scientists to design systems that rely on stable magnetic behavior. Motors, generators, sensors, storage systems all depend on the reliable response of materials to magnetic influence. And this reliability is not imposed externally. It arises naturally from the underlying physical laws. Another layer of reflection appears when considering how magnetic systems return to equilibrium after being disturbed. If a magnetic system is altered, it does not remain in that altered state unless conditions support it. It tends to relax towards stable configurations. Alignments re-establish, fields redistribute, balance is restored. This tendency toward equilibrium is not unique to magnetism, but magnetism expresses it clearly. A disturbed system seeks a stable arrangement. A structure adjusts until internal and external influences are balanced. This creates a sense of continuity even through change. The system does not break. It evolves. It reconfigures. It maintains coherence through adjustment rather than resistance. As this idea is followed further, it becomes natural to think of magnetism as part of a broader principle of relational stability. Systems are stable not because they are rigid, but because they are capable of adjustment. They maintain structure through responsiveness. They remain coherent through interaction. And magnetism is one of the clearest physical examples of this kind of stability. Even at cosmic scales, magnetic structures do not exist in isolation from change. They evolve alongside the systems that generate them. They respond to motion, energy, and shifting conditions, and yet they persist as recognizable patterns over time. This persistence through change is what gives magnetism its quiet sense of continuity, not frozen, not static, but enduring through adaptation. As the reflection gradually settles, there is no final conclusion emerging, no endpoint where magnetism becomes fully contained or fully explained in a single thought. Instead, What remains is a sense of ongoing structure, a framework that appears again and again across different levels of reality, a pattern of interaction that does not require attention to continue existing, always present, always active, always quietly shaping the world through invisible relationships that extend across space and time. As this reflection continues further, something subtle begins to happen with the idea of magnetism itself. It starts to feel less like a phenomenon that exists out there in the world, and more like a way the world remains continuously organized. Not an event, not a single interaction, but an ongoing condition of structure and relationship. At this stage, it becomes useful to notice how often magnetism depends on alignment. Alignment of spins, alignment of domains, alignment of motion with field direction. Alignment is not a dramatic process. It is quiet, gradual, often invisible unless you are looking closely at the system. And yet, in magnetism, alignment is everything. When microscopic elements align, large-scale magnetic behavior emerges. When alignment is disrupted, that behavior weakens or disappears. So what appears as a strong, unified force at the surface is actually the result of countless small alignments working together beneath. This creates an interesting contrast: strength arising from order, order arising from cooperation, cooperation arising from local interactions. There is no single central source of magnetism inside a material in the way intuition might expect. Instead, there is distributed organization, a collective pattern built from many small contributions, each one simple, each one local, but together forming something much larger and more coherent. This idea of collective emergence is one of the most important concepts in modern physics, and magnetism offers a clear and accessible example of it. A refrigerator magnet does not rely on a single dominant particle or structure to create its field. It relies on the cumulative alignment of many particles across a region of material. When those alignments are stable, the magnetic field persists. When they are disrupted, the field weakens. This dependence on internal order gives magnetism a quiet fragility and strength at the same time. Fragile, because it depends on alignment. Strong, because when alignment is maintained, the resulting field is stable and consistent over time. This dual nature appears again and again in physical systems. Order requires conditions to be maintained, but once established, order can persist with remarkable stability. Magnetism sits comfortably within this balance. As attention shifts outward again, the same principle can be seen at larger scales. In planetary systems, alignment plays a role in how magnetic fields form and persist. In stars, alignment of charged particles and flows of plasma contributes to large-scale magnetic structures. Even in galaxies, magnetic fields are shaped by organized motion of matter across vast distances. In each case, large-scale behavior emerges from distributed alignment at smaller scales. There is no single point of control, only patterns of interaction that reinforce one another over time. This raises an interesting way of thinking about structure in general. Structure is not always imposed from above. It often emerges from within, from local rules, from repeated interactions, from simple behaviors accumulating into larger patterns. Magnetism expresses this principle in a particularly clear form, because the results are so measurable and consistent. A change in alignment produces a change in field. A change in field produces a change in motion, and this loop continues as long as the system remains active. Another important aspect of magnetism is how it interacts with energy. Magnetic fields do not exist independently of energy flow. They are closely tied to movement and change. Whenever charges move, energy is involved. Whenever fields shift, energy is redistributed. This means that magnetism is not static in an energetic sense. It is part of a continuous exchange. Energy is not created or destroyed by magnetism alone. It is transformed, redirected, reorganized. This transformation is subtle but constant. It happens in electric motors, where magnetic fields convert electrical energy into motion. It happens in generators, where motion is converted back into electrical energy through magnetic induction. It happens in countless systems, where fields guide the flow of energy from one form to another. In this way, Magnetism acts as a mediator of change, a structure through which energy finds new configurations. And this mediating role is not limited to human technology. It is present in natural systems as well, in Earth's core, in solar activity, in cosmic plasma flows. Energy and magnetism are deeply intertwined. They cannot easily be separated in practice. They form a coupled system of motion and field. As reflection continues, another layer emerges. The idea that magnetic fields are not objects in the traditional sense, but descriptions of relationships. They describe how space behaves in the presence of certain conditions. They define how influence is distributed. They map how motion will respond to alignment and position. In this sense, a magnetic field is less like a thing and more like a rule expressed across space, a rule that tells matter how to behave when certain conditions are met. This reframing is subtle but important because it shifts magnetism from being something added to space to something that describes space under specific conditions. Space is not passive in this view. It has structure, and that structure determines how interactions unfold. This is why magnetic fields can extend through empty regions without losing meaning. Even in regions where no matter is present, the structure of the field still exists as a description of potential interaction. It is only when matter enters that region that the field becomes directly observable through motion and force. This idea of potential structure is one of the deeper aspects of field theory. It suggests that reality is not only defined by what is currently interacting, but also by how interaction would occur if conditions changed. Magnetism provides a clear example of this. A field exists whether or not a test object is present. Its properties are defined independently of observation, but its effects become visible only when interaction occurs. This separation between existence and detection is subtle but important. It reminds us that observation is always mediated. We never see the field itself directly. We see what the field does to something else. This indirectness is not a limitation. It is a feature of how physical understanding is constructed. We learn about structure through interaction. We infer invisible systems from visible outcomes, and magnetism is one of the clearest examples of this process in action. As the reflection gently continues, it becomes harder to isolate magnetism from the broader fabric of physical reality. It is no longer just a topic among others. It becomes a recurring pattern, a consistent expression of how interaction, alignment, and structure combine across scales, from microscopic particles to planetary systems, from quiet materials to active stars, from simple objects to complex technologies. The same underlying behavior appears in different forms, always governed by the same principles, always expressing continuity through change. And as this awareness settles, there is no need to conclude or resolve anything, because magnetism does not conclude. It continues. It persists as long as the conditions for interaction exist. It adjusts. It responds. It maintains structure through balance. And it remains, quietly, as part of the ongoing organization of the world.